Welcome everybody to the last session of today. The first paper is Conditional Random Field Autoencoders for Unsupervised Structured Prediction. The authors are Waleed, Ammar, Chris Dyer, and Noah Smith from CMU. And Waleed is going to present. Please, let's welcome Waleed.
Hello, everyone. My name is Waleed Ammar, and I am a PhD student at Carnegie Mellon University. This is joint work with my advisors, Noah Smith and Chris Dyer. This talk is about a new approach to do unsupervised structured prediction, which we call CRF autoencoders. The main message I'd like to get across in this talk is that if you want to do structured prediction with engineered features and train with unlabeled examples, and you want to do that efficiently, you should consider using CRF autoencoders. So let's start with a less ambitious goal. If we want to do these things, but we only care about training with labeled examples, we can use a conditional random field. CRFs sound like a good starting point to achieve what we really want, which is train with unlabeled examples. They model the structured output y given the structured input x, and we train them by maximizing the conditional log likelihood of y given x for all xy pairs in the training set. For example, this is a linear chain CRF, which can be used to do sequence labeling. Here, every label is directly dependent on the neighboring labels and the corresponding observation. We like CRFs because the partition function marginalizes only the y's, but not the x's. So the x's tend to be in a much larger space. This gives us a lot of freedom in defining features with global scope in the input, as long as we keep the tree width within the elements of y small. For example, we can add some dependencies between the label and the previous word. This is all going to help us define more regularities that we expect the model to discover. So this all works well when we only want to train with labeled examples. But when we want to learn from unlabeled examples, we don't observe y in training, so this supervised objective is no longer feasible. Perhaps we can use the autoencoder architecture to ground the output y to regenerate, to reconstruct the input again, which here I will call x prime. So we came up with this new objective, which looks like the CRF objective, except now we're marginalizing out the y's and multiplying n the probability of reconstructing x prime conditional on y. So from now on, I'll be calling the first part of the model, y given x, the encoding part, x prime given y, the reconstruction part, and I'll be calling y the latent variable or the hidden layer. So as a concrete example, let's start with the CRF that we looked at before. And then we will make every label regenerate a copy of the observation at the same position. Hence the name CRF autoencoders. Basically, it's an autoencoder that uses a conditional random field as its encoding model and some other model for reconstruction. So CRF autoencoders differ from traditional autoencoders in several ways. For example, in the CRF autoencoders, there is a structure among hidden variables, but we must define this structure such that the partition function of the CRF is tractable. Also, in CRF autoencoders, the hidden layer directly represents the output we're trying to predict, which can be directly evaluated against gold labels. This is not to say that CRF autoencoders are better or worse than traditional autoencoders. They are just meant for different purposes. So traditional autoencoders are great for finding a distributed representation of the input, while CRF autoencoders are great for unsupervised structured prediction. So what do we mean exactly by structured prediction? We're interested in problems where the output we're trying to predict consists of several variables with direct dependencies among themselves. So yi and yj may not be independent given the input x. Examples include the NLP problems where the input is usually a sequence of words and the output may be a sequence, a tree, or a graph of syntactic or semantic categories. Other structure prediction problems include object recognition, predicting the secondary structure in proteins, and selecting which ads to show users so that they are more likely to click. For the purpose of this talk, I'll be talking about parse-speech induction or tagging. Here, the input is a sequence of words, and the output is a sequence of syntactic categories. And since we're interested in unsupervised learning, the training data will only consist of the X's but not the Y's. So what are some existing solutions to unsupervised structure prediction? The mainstream approach for unsupervised structure prediction is to define a joint model of X and Y and maximize the likelihood of input examples marginalizing out the Y's. We will talk about 3 models which vary in their parameterization and ability to use features, and we'll give them colors. So there will be the blue model, the purple model, and the red model. The blue model is a first-order hidden Markov model where each label generates the corresponding observation and generates the following label. We like HMMs because they're fast, but we don't like them because they generate the observations using what we like to call stupid multinomials or categorical distributions. They are stupid because they don't share statistical strength among related observations. For example, in POS tagging, we'd like the model to learn that words which start with a capital letter are more likely to be labeled as proper nouns. This is not possible in standard HMMs. Which leads us to the second model, which is a modification of our HMM that replaces the stupid multinomials with logistic regression multinomials. Now we can have some local features that fire every time a word that starts with a capital letter is labeled as a proper noun. This model is reasonably fast, but it can be slow in problems like word alignment, where we need to estimate the probability of probability of every word in the target language given each word in the source language. The other bad thing about this model is that we cannot encode non-local features like these ones. So the first indicates that the word that comes before the word san tends to be a preposition, and the word that comes after the word san tends to be a proper noun. You think these features would help because the word san is the first word of several named entities. But the purple model, if we want to use these features, will incur a huge cost, a huge runtime cost. So finally, the red model is the class of joint undirected models, or MRFs. We added all dependencies we care about so that we can define the features we're interested in. So now we managed to add both local features and non-local features. So that's great, except that this model is extremely slow because the MRF partition function, which marginalizes both the Y's and the X's. So in summary, for joint models, the blue model doesn't share statistical strength between related observations. The purple is slow at times, and it doesn't allow global features. And the red model is extremely slow. So now we get back to the CRF autoencoders. We mitigate the problems of feature-rich joint models by coming up with this construction, which allows us to define features with global scope in the input without slowing down the inference. This is possible because the partition function in the CRFs is tractable because it only marginalizes Y. So we talked enough about the encoding part of the model. So let's talk about the reconstruction part. What is X prime and how do we reconstruct it? Obviously, this is going to be dependent on the problem we're trying to solve. So in POS tagging, we tried 3 things. First, we let X prime be an exact copy of X and use the categorical distributions to generate them. So if you squint your eyes, you'll see that this looks a lot like an HMM, except that the dependencies between the Y's are now unidirectional. The second thing we tried is to generate the pre-trained word clusters instead of the actual surface forms of the words. intuitively, we should use representations of the input which can be generated from the hidden layer with low entropy. So we used Brown clusters, which tend to encode some syntactic information about the words. The third thing we tried is to let X prime be word embeddings and let the reconstruction model be a multivariate Gaussian. So optimization in this model is pretty straightforward. We first initialize the parameters of the encoding and the reconstruction model, lambda and theta. And then we use block ordinate descent to alternate between optimizing lambdas and optimizing thetas. So when we were optimizing lambda, we use LBFGS, and when we were maximizing the theta, we use expectation maximization. So before I move to results, I'd like to share a few thoughts about why we think this might work. First, note that the hidden layer consists of variables in a smaller space than the input variables. So in sequence labeling problems, for example, it's typical for the number of unique labels to be much smaller than the number of unique observations. So when we maximize the conditional probability of regenerating the correct observation via the hidden layer, which lives in a much smaller space, we are necessarily creating an information bottleneck and pushing the model to find regularities. However, finding these regularities is easier said than done. It's common for models which we use for unsupervised learning to pick up some regularities but not the regularities that we are interested in. For example, models may pick up some semantic classes instead of syntactic classes, or vice versa. So the nice thing about CRF autoencoders is that we have now more leverage over what regularities the model may potentially discover by defining the appropriate features in the encoding part and using an appropriate representation in the reconstruction part. Essentially, we're building in useful inductive bias to help the model find the kind of regularities we want. One caveat here is our intuition about features is not always correct. So we may add some features and find that the performance drops. So it's important still to do some model selection to find which feature sets are good. But a good starting point for the feature set is whatever feature set people have been using for supervised learning in this task. Okay, finally, our empirical results. So in word alignment, we were not able to compare it to any other feature-rich models because they are too slow. This plot shows the time it takes to do exact inference in one sentence as a function of the corpus size. When we use the red model, larger corpora with larger vocabularies result in much slower inference, while inference in CRF autoencoders stays close to 0 all the time. So instead we compare the CRF autoencoder model to word alignment tools that are commonly used in state-of-the-art machine translation systems. So in intrinsic evaluation, we found that CRF autoencoders reduced the alignment error rate by 12% compared to the best of the two baselines we use, which are Giza++ and FastAlign. In end-to-end translation evaluation, we found that CRF autoencoders was competitive, outperforming both baselines in Czech English and in Urdu English, but gave worse results on Chinese English. And when I diagnosed what's wrong with Chinese, I found that several helpful features which helped with Czech and Urdu were orthographic features, and the Chinese language does not use letters. So we anticipate that adding more features or doing more feature engineering might help fix this problem. So now the part-of-speech induction results. We tuned using an English dataset and tested with 7 other languages. We found that the CRF autoencoders outperform both the blue and the purple models on average and in most languages. We recently got better results when we used a Gaussian reconstruction model, but they're not in the paper, so I'll save them to a different talk. So in conclusion, CRF autoencoders allow us to efficiently learn from unlabeled examples in structured prediction problems where feature engineering plays an important role. We're currently working on a few extensions, trying to characterize the class of structured prediction problems which can benefit from CRF autoencoders and adding more supervision in the form of labeled examples or soft constraints. So stay tuned.
Joshua.
It seems to me that compressing the X information into the labels Y loses too much information for the autoencoder idea to be as useful as if you had, in addition to Y, some other latent variable which would capture sort of the rest of the information that's not in Y, but that's in X. Otherwise, what's going to happen typically, I would expect, is that what you generate with your decoder is basically just a template for that particular value of Y in X space, which doesn't seem very useful.
I agree. So in the word alignment model, I didn't show this, but in the word alignment model, we actually do condition on what we call signed information, which is available in both parts of the model. So both in the encoding part and the reconstruction part, we can condition on more variables that help us make a better prediction for X prime given Y. So we do use this, but we have to make it in a controlled way. Otherwise, it will be trivial to just reconstruct X prime given X directly.
So I don't understand, what is that signed information? It's some function of X?
It will be dependent on the problem we're trying to solve. So in word alignment, for example, the word alignment task is to find alignment between words in the target language and words in the corresponding translation in the source language. So here what we have is X prime is the target language, is the target sentence, and the side information is the source sentence. So we get to condition on the position. YI is the position in the source sentence where each target word is aligned. And we also condition on the sentence, in the source sentence, so that we can index. So when we're reconstructing the first word in the target sentence, we know that it comes from the fifth word in the source sentence, and we have the source sentence to look into and extract features. No, here we don't extract features, but potentially we might.
Any other question? Have you thought about an extension for continuous variables? For? Continuous variables?
We're trying to find more. We're trying to find more problems that might potentially benefit from this, including some tasks that would require Y to be continuous. But I haven't started working with that.
Okay, let's thank Waleed again.